Good morning. We are going to talk about the so-called dot product on Rn. It's a special case of inner product on vector spaces. So this particular thing will be very, very concrete, dealing only with Rn. This is for various reasons. First, it's an easy thing to work with. And second, this is very much needed when you want to go to several variable calculus, analysis on Rn, etc. And the third, when you want to look at, let's say, metric spaces, the so-called Euclidean distance between 2 points in R2 or R3 or Rn requires some idea about Cauchy-Schwarz inequality and the triangular inequality, etc. So that is why I made this a separate thing. But then, as you can see, you can use it in many subjects. Okay, let us get started. Let us hope that I will be able to do it in about 15 minutes. Let us start sharing the screen. Okay, as usual, the best reference here would be my linear algebra. But so I'm not going to spend time on the geometric aspects of inner product or the dot product here. Okay, I just want to be quick thing. But when we do inner product spaces in linear algebra, then we will look at these things a little more geometrically. Here, I just want to correct the basic facts. Definition of dot product, followed by norm, and followed by Cauchy-Schwarz inequality and the triangular inequality and the Euclidean distance. These are the points which I want to cover in this lecture. So let us get started. So I have Rn. So all of you know what is Rn. Rn stands for set of all x, which is, you write it as n tuple in Rn. Okay. This is not a very good way of saying, but anyway, x in R, xj in R. Okay. But sometimes I also like it to write it as x1, x2, xn as column vectors, but it all depends. Okay, right. Now, what is the dot product? So start with any two vectors x1, y in Rn. Then I want to define x dot y. You read it as x dot y. Okay. It's also sometimes known as scalar product, but anyway, let us call it a dot product. So what is x dot y? Okay. What is y? Y will be y1, y2, yn. And x will be x1, x2, xn. Therefore, this is nothing other than x1, y1 plus x2, y2 dot dot plus xn, yn. So in some shorthand notation is xj, yj, j running from 1 to n. It's also somewhat very useful when I have to deal with a matrix and a vector. Okay, so this is same as, think of this row vector as 1 cross n matrix, right? Therefore, this is a row vector and y is also a vector. Therefore, this will be a column vector of size n cross 1 and make it. What will this be? This will be an 1 cross 1 matrix. This matrix is nothing other than, it has only one element, namely xj, yj, j equal to 1 to n. Okay, this interpretation could be useful later, but I don't need it now. Okay, do all of you understand what is the definition of dot product? So in the case of R2 or R3, okay, I usually write xy, x1, y1, z1 and x2, y2, z2 for two vectors here. Then the dot product will be, call this as a vector u, call this a vector v, then u dot v, we will write it as x1, x2 plus y1, y2 plus z1, z2. Because when it comes to R1, R2 and R3, we usually use the coordinates as xy, xyz, etc. So in that case, we have to rewrite. But that's nothing. Okay, very good. Now we want to study the properties of the dot product. Let us look at it. The first thing is, suppose x is a vector in Rn. Okay, what is x dot x? X dot x is summation x xj squared, right? Because this is, look at that, x1 x1 plus x2 x2 plus xn xn, y xn xn. Therefore, it is x. Okay. Now these are all real numbers. Therefore, this is greater than or equal to 0. Is that clear? So for every x in Rn, x dot x is always greater than or equal to 0. That's the first observation. Second, suppose when I want to know when x dot x equal to 0, when does it happen? This happens if and only summation xj squared is 0. Okay, this is sum of non-negative numbers. Therefore, this happens if only if xj squared is 0 for every j. But this happens if only if xj is 0 for every j. But this happens if only if x equal to 0 as a vector. Okay, this is a 0 vector. That is x equal to 0, 0, 0. This is a 0 vector. Do all of you understand this? Okay. So what are the properties we have found out? For any vector x dot x is greater than or equal to 0. And if x dot x equal to 0, then x must be 0. And it's an if and only. Do you see that? If x is 0, then it will be 0 squared. Summation 0 squared j equal to 1 to n. Therefore, this is an if and only. Therefore, x dot j is 0 if and only if x is 0. Do all of you agree with that? Okay. The next one is, since we are in a vector space, Rn is a vector space, right? What are the two operations available? Namely, vector addition and a scalar multiplication. So we would like to know how do the dot product behaves with respect to the vector algebra operations, namely vector addition and scalar multiplication. Before that, let us look at what is x dot y and y dot x. X dot y is summation xj yj. I am not writing j equal to 1 to n, okay? And y dot j is yj xj, right? But notice that this summand, okay, and this summand are the same because xj yj are real numbers and product is commutative in real numbers. Therefore, the xj yj is same as yj xj. Therefore, summand wise each one of them equal. Therefore, the sum are also equal. Do you understand? Therefore, we found this. Okay, right. Now let's go to the point which I wanted to say. Let's look at the scalar multiplication. Suppose t is a scalar, x and y are vectors. Okay, then I can take t dot x. This is tx is stands for scalar multiple of x by the scalar t, and there is a vector y. You understand? Similarly, I can do x dot ty also. You follow that? Okay. And now let us look at what is tx. This is by definition tx1 txn. Therefore, tx dot y equal to the first coordinate of tx, which is tx1. Okay, maybe write it tx1 times the first coordinate of y, which is tx1 y1. Next will be tx2 y2 and so on txn yn. That is t times x1 y1 dot dot xn yn. That is same as t dot to x dot y. Now you should understand what is x dot y. This is a real number. T is a real number. This is a product of two real numbers, right? Okay. But in a similar fashion, you can see x dot ty is also equal to x1 xn ty1 tyn. So that's going to be summation xj t yj j 1 to n. But remember two things. Product is commutative in real numbers and also the product is associative. Therefore, tyj I can write as xt, I can write xj t, I can write it as txj. Therefore, this is same as t xj yj. Therefore, t times x dot y. Yeah. So what you have found is tx dot y is same as x dot ty, which is same as t times x dot y. You should understand. Don't get confused. This is a vector. Dot product with that vector. This is a vector. This is a dot product with the vector. Whereas this is dot product x and y, but then I get a real number. This is a real number. So these three real numbers are equal. Okay. Now what is the next one? The fifth one is what I said about vector addition. So suppose I have three vectors x, y, z in Rn. Then I can look at what is x plus y dot z. Remember x plus y, this is a vector in Rn. Therefore, it's dot product, I can do that. Okay. So the very interesting thing is, similarly, I can ask for x dot y plus z also, right? So the very interesting thing is, as a mnemonic, you should remember the distributive law of multiplication or addition in real numbers. This is x plus y dot z. Think of this real number, that will be x times z. That is, I will write it x dot z, and y times z, I will write as y dot z. That's the only thing. So I expect this to be the same. Similarly, I expect this to be x times y, therefore x dot y plus x times z, that is x dot z. Okay, so we will prove one of them, the other one is similar. Okay, right. So let us prove this. X plus y, what is x plus y? It is x1 plus y1, etc. xn plus yn. Therefore, x plus y dot product with z. Therefore, this is dot z1, z2, zn. That is equal to x1 plus y1 times z1. Right? This is the first vector of the x plus y. Sorry, first coordinate of x plus y, and the first coordinate of z, namely z1. Plus similarly second, x2 plus y2 into second coordinate of z, that is z2, and so on. But what is this? This, you can see that why I said this is like distributive law. This is ordinary. What here? This is nothing other than what happens in real number system. X and y1, x1 and y1 and add, and z, it's multiplied with z1. Therefore, the multiplication distributes over addition. Therefore, it is x1 z1 plus y1 z1 plus this term. This is x2 z2 plus y2 z2 plus xn zn plus yn zn. Right? Now, what do you think I want? Remember, I want to show this is equal to this. Therefore, what will I do? These are our real numbers. Associative to commutative. Addition is associative and commutative. Therefore, I can correct the terms which x dot z is involved. That is, these are the things I will look at: x1 z1, x2 z2, xn zn, and then I will look at the other terms: y1 z1, y2 z2, yn zn. Then what will I have? I'll have this as x1 z1 plus x2 z2 plus xn zn. Okay, this is the first number. And second one, what will I do? I will add them to be this y1 z1 plus y2 z2 plus yn zn, this. But what is this? So this is equal to nothing other than x dot z. This is nothing other than y dot z. So have you proved it? Yeah? No. So similarly, this you should check. Okay, it's easy, but to become confident, it's good that you do it once. Okay, if you see me doing, you may not get the confidence. Only if you do it, you will get the confidence. So you should do it. Okay, now let's combine all these things together. Right? See, for example, this will also follow from this because of the symmetry. X dot y plus z is same as y plus z dot x, because of y condition 3. Okay, by 3. This is by 3. Right? But now I know y plus z is this is y dot x plus z dot x. Yeah. So, but again by symmetry, y dot x is same as x dot y plus x dot z. So we have got it. You understand this? Yeah. We got this one the same as here. Okay. But I would suggest you do it in the long way at least once so that you become confident. But remember my mnemonic. Okay. Even though algebra teachers would frown upon that, it's very easy because I know many students, even at MSc level, they struggle to do this. The easy thing is think of this: x plus y dot z is, think of this distribution: x plus y is multiplied by z, that is same as x times z. But the only thing is I don't say times. I will simply write x dot z because x is a vector, z is a vector. Similarly here. Do you follow that? If you think you understood, let me ask you a question. What is ax plus by? Okay, a, b are real numbers, c, d are real numbers, x, y, z, x, y, u, v, these are all vectors in Rn. Cx, cu plus dy. How will you do that? Remember what I said? Think of this ordinary distributive law multiplication. This will be AX times CU, right? But remember A and C are real number. Therefore, A that will come out. And X times U, but X times U, how should I write? X dot U. You understand this? Please pay attention. I am multiplying this two. Next, what will I do? I will multiply this with this distributive law, right? Therefore, that's going to be AX dot dy. Okay, but that is, I will write it as AD x dot y. You follow that? AX CU. Oh, this is B. Sorry for the goofing. I forgot what I wanted. Let me again start. AX plus, no, I don't want this. AX plus BY CU plus DV, not Y. Therefore, AX dot CU, this is one vector. Okay, so there I am using this factor. Yeah, if you want, let me again do that. AX plus BY dot product with CU plus AX plus BY dot product with DV. You understand that? This is a single vector, some vector, dot product with some sum of two vectors. Therefore, this vectors distributes over these two vectors. You follow that? Now we use this. This is sum of two vectors. AX is a vector, BY is a vector, CU is another vector. Therefore, that is AX dot CU plus BY dot CU. Similarly, AX dot DV plus BY dot DV. Okay, I am thinking of this one, ordinary multiplication. But remember, A is a scalar, C is a scalar, this dot x. And what did we find out? We found out that t times x dot y is same as x times t dot y, and both are same as t times x dot y. In particular, I have Rx plus Sy. This is same as R S x dot y, which is Rs x dot y. You understand this? So this is going to be AC into x dot u plus BC into y dot u plus AD into x dot v plus BD into y dot v. Okay, please check all these things, pause, review, and proceed. Okay, if you simply watch me doing, you will never get confidence. That's what happens to many students, because when I teach MSc, I find that students are not very comfortable with inner product because they never worked out these kinds of stuff. But there is a mnemonic, as I said, keep that in mind, then that makes life easy. Okay, good. So I want a very special case of this now in our Rn case. So in particular, what do you think x plus y dot x plus y is? Remember, our mnemonic should say x squared plus xy plus yx plus y squared, right? So how will I write it? X dot x plus x dot y plus y dot x and y dot y. You understand this? But remember, x dot y and y dot x are the same because of symmetry. Therefore, it is x dot x plus 2 x dot y plus y dot y. Do you like it? It's like x plus y whole squared is x squared plus y squared plus 2xy. Yeah? Okay, please again review. Make sure that you understand. Okay, these are all very easy. And do not be intimidated by n tuple, etc. Think of it this way, you won't get confused. Okay, so these are the properties. Now we want to define a new object called norm of a vector. Norm of a vector is this is, remember, x dot x is non-negative, therefore it's there is a unique non-negative number whose square is x dot x. So we define norm of x to be the unique non-negative square root of x dot x. Since x dot x is non-negative, this exists. So this is called norm or length of a vector. Okay, in the case of R2, okay, if you think of like this, you will see this is a vector xy. Okay, what is the length of this? Length of this vector is This is x, this is y, x squared plus y squared and root of this by Pythagoras theorem. Okay. So in generalization of that, we are doing it in Rn. All right. Now comes the next important thing. Okay. There is a what is called Cauchy-Schwarz inequality. So PRP. Yeah, before Cauchy-Schwarz inequality, when can x dot x be? When norm could be 0? That means x dot x is 0. Because the x dot x square root is 0. That means x dot x is 0. But remember our first condition or second condition, x dot x is 0 if and only if x is 0. Therefore, this happens only if x equal to 0. All right. Okay. Keep that in mind. What does it say is given any two vectors x, y in Rn, then I have x dot y. Okay. This is a real number. Right. Now, what Cauchy-Schwarz inequality says is this x dot y in absolute value is less than or equal to norm of x into norm of y. This is true for every xy. You follow that? It gives an estimate for the inner product in terms of the length of the vectors. Okay. This again you will see in my book. I explain in terms of trigonometric formula for the sides of a triangle. But let's not worry about. As I said, I will stay away from geometry for a while. Okay, which is very unusual for me. But anyway, this is what you do. This is what you want to prove. And also it says equality holds if only if okay one is a multiple of other. Multiple of the other. One of them, not each of them, one of them. Okay. Okay. Before we go further, let us try to understand. If one of them is 0, if x is 0 or y is 0, the result is obvious because x dot y, if x is 0, what is x dot y? It is 0 because summation xi into yi, xi is always 0 or yi is always 0. Therefore, it is 0. You follow that? Therefore, and this is what is norm of x, then it is 0. If x is 0, x dot y is 0 and norm of x is 0, therefore this inequality is obviously true. You follow that? Okay. And similarly, y is 0. Therefore, we assume x is not equal to 0 and y not equal to 0. So we need to prove this result only in this case. What is the trick? The trick is very simple. What you want to do? You want to show if equality holds if and only if one is a scalar multiple of the other. Okay. All right. Let us assume my x is t times y. The vector x is. That means what? X minus ty is 0. That means x minus ty, okay, dot product with x minus ty must be 0. You follow that? Because if and only if norm of x minus ty whole squared is 0. Right? This happens if and only if this. That's our second condition. Right? You follow that? So we want to start with this object and try to see what we can do. Okay. This means this. Okay. When this happens, this is happens if only if xj minus t times yj whole squared j equal to 1 to n. This is 0. Right? Okay. This is the one which motivates us to define the following function f from real numbers to real number. So we are fixing x and y in Rn, and x is not equal to 0 and y is also not equal to 0. In fact, one of them is not 0 is good enough for our purpose. Okay. What is this? This is f of t for any real number. I am defining x minus ty dot product with x minus ty. So in all its glory, if you expand this, this is what it is. You understand this? Are you following? Because x minus ty is xj minus t times yj dot product with that. That is xj minus tyj whole squared. Okay. Do you follow this? Okay. But we don't need it. We will work with this. Okay. This may even be slightly confusing, but this is much easier. You will see. What is this? This is x dot x. Next is x dot minus ty. Therefore, minus t times x dot y. This is over. Next, this fellow has to distribute over the next one. That is going to be minus t times y dot x, and then minus ty times minus ty, which is same as saying plus t squared times y dot y. Do you understand this? How I got it? If you write like this, you'll have a lot more time to write, whereas this is much easier. See, that is the advantage of vector notation. Unless needed, don't work in terms of coordinates or components. Okay, as far as possible, think of this. Learn to work with this kind of thing. You will become happy and you will not be intimidated by too many symbols surrounding you. Okay, they will smother you. Now, what do I know? X dot y is same as y dot x. Therefore, I can rewrite it as x dot x minus 2t times x dot y plus t squared times y dot y. Do you understand this? Now, this is a function of t. Remember, x and y are fixed. Therefore, this is a constant. This is a constant. This is a constant. Okay. So, what do you find out about f of t? It's a polynomial. In which variable? In t. It's a real variable. X and y are not, they are fixed vectors, not even numbers. Okay. You follow that? Right. Now, what do I want to do? Remember, this is y dot y. Remember, y is non-zero. Therefore, y dot y is positive. Therefore, if you know your analysis, you know that f of t goes to infinity as t goes to infinity. Remember, I don't need any of these things for what the proof. Okay. But it's my habit to understand in depth what we are learning. Okay. So I'm teaching you. So if you want, you can ignore this. Right. There, and remember, f is also differentiable. It's a polynomial function of 2. Okay, quadratic polynomial in t. It's a differentiable and it goes to infinity because y squared, okay, the t squared term is positive. The coefficient is positive. Therefore, it will go to infinity as t goes to plus or minus infinity. Okay, at both sides it will go to, right, and it's continuous. Therefore, you can say if at all you should have a minimum. It cannot have a maximum because it keeps going to infinity. So how do I find it? All these things you can ignore. Simply take, I want to find the critical point. That is, I want to find t at which f dash t is 0. Let us do that. Now remember, x dot x is a constant. So when I differentiate this with respect to this is 0. Minus 2t times x dot y. Remember, x dot y is a constant. Therefore, minus 2x dot y into d by dt, the derivative of t, which is 1. Plus, same reason, y dot y into 2t. Right? Derivative of t squared. Okay. So when is this 0? This 2 I can cancel. Therefore, okay, f dash t is 0. If and only if t times y dot y must be equal to x dot y. Okay. Please pause, review, proceed. Okay. So let t naught equal to x dot y by y dot y. Now, how can I do that? Because I know y dot y is non-zero. Therefore, y dot y is strictly positive. You follow this? Okay. All right. Okay. Now let us compute what is f of t naught. What is f of t naught? F of t naught is, okay. Uh, let us just substitute here x dot x. Yeah. This is good enough for me. See, f of t naught, f dash t we had computed. Therefore, this is going to be t naught. Therefore, 2 times. Oh, f of t naught is all. Not f dash. I want this. Sorry. I'm looking at this. This is f of t. Right? Yeah. Okay. That's what we are doing. That is going to be x dot x minus 2t naught. 2t naught is 2 into x dot y by y dot y. Okay, 2t naught into x dot y. Therefore, it's x dot y whole squared into x dot y. Do you understand this? This is t naught. Sorry, not this one. This is T naught. Okay. So minus 2 T naught into x dot y. The T naught into x dot y. Okay. Plus T squared. T squared is x dot y whole squared by y dot y whole squared into y dot y. Right? Yes. Okay. Notice that what is f of t? F of t is x minus ty dot product with x minus ty. And what is the first property of the dot product? It is always greater than 0. In particular, f of t naught is greater than equal to 0. That means this guy, okay, this expression is greater than equal to 0. But now remember, there is a y dot y, therefore this cancels. So y dot y is common, all right? And y dot y is positive, therefore I can multiply both sides of the inequality. What is the inequality I have? X dot x minus 2 x dot y whole squared by y dot y plus x dot y whole squared by y dot y. This is greater than or equal to 0. But this is minus 2. This is just. Therefore, this is x dot x minus x dot y whole squared by y dot y is greater than or equal to 0. Do all of you agree with that? Yes? Okay. Therefore, again cross multiply this by y dot y. That means x dot x into y dot y is minus x dot y whole squared is greater than or equal to 0. That is x dot x, which is norm x squared, y dot y, which is norm y squared, is greater than or equal to x dot y whole square, which is mod x dot y whole square. All right. So we are almost through. What did we want to prove? We wanted to prove mod xy is less than or equal to norm x into norm y. Did we get it? What we got is in terms of square. But then there is another analytical fact we need. Suppose a and b are non-negative numbers. Then a is greater than or equal to b if and only if a squared is greater than or equal to b squared. In fact, this is also true for any positive natural number, any natural number. Why this follows? Okay, that is because a squared minus b squared I can write as a minus b into a plus b. Remember, a plus b is non-negative, therefore then is non-negative. Therefore, sign of this fellow depends on the sign of this fellow. Therefore, if a is greater than b, then a squared minus b squared is also greater than 0. That is, a squared is greater than b squared. You understand? Pause, review, proceed. Therefore, this implies this. So this is Cauchy-Schwarz inequality. Okay, right. Now this is equal to 0 implies x minus ty must be 0. Okay. When does the equality hold? If and only if this is equal to 0. That happens if and only if x minus ty dot x minus ty is 0. That means x minus ty must be 0. That means x equal to t times y. Okay, we proved the equality part also. Okay, please check. Okay, f of t naught is 0 if and only if x minus t naught y is 0. That is if and only if x equal to t naught y. Okay, equality holds in Cauchy-Schwarz inequality if and only if f of t naught is 0. That is if and only if x minus t naught is 0. That is if and only this. Okay, I very briefly explained, but you should convince yourself. Okay, check. Okay, don't accept me what I'm saying. Please check. But anyway, the major point is we have proved Cauchy-Schwarz inequality. Okay, now what do we do that? So once we have done, what we can do is we can prove the so-called triangle inequality for the norm. So remember, this is your x and this is your y. So this is x, this is y. Then you know how to compute x plus y. right? So what it says is norm of x plus y is less than or equal to, again, you know why it is norm. Okay, because this is the length of this vector, and this vector and this vector have the same length, and this vector and this vector have the same length, and this vector is the length of this vector is norm of x plus y. So what are we saying? Norm of this vector is less than or equal to norm of this vector, the length of this vector plus length of this vector. So that is why it's called a triangle inequality. Okay, but that is obvious. Why it's obvious? Notice that this happens. This is true if and only if, as just now I explained, if I square it, it should happen. I am using this, right? These are all non-negative, so this a is less than or equal to b if and only a squared is less than or equal to b squared. You follow that? Okay, now let us do this. What is this? Norm x plus y whole squared. Okay, this is norm x squared plus norm y squared plus 2 times norm xy. Norm x into norm y. Right? This is this object. What is this object? This is x plus y dot product with x plus y. But I know how to deal with this. Now I think all of you are comfortable. What will you do this? X times x, that is x dot x, plus x times y, that is x dot y, plus y times x, that is y dot x, y times y, which is y dot y. But that is x dot x, that is norm x squared, and x dot and y dot x are the same, therefore 2 times x dot y plus norm y squared. So I want to show this object is less than or equal to this object, right? This object is less than or equal to this. X squared cancel, y squared cancel. So I should know 2 is also I can cancel. X dot y is less than or equal to norm x into norm y. Yes, even in modulus is true, right? This is less than or equal to modulus x dot y, but that's less than or equal to norm x into norm y. Therefore, I have proved it. Okay, please review. Okay, right. Now, where does it come to the so-called Euclidean metric? See, we have what is called Euclidean metric. Usually, I denote it by D2 on Rn. How is it defined? I define D2 of here two vectors x and y to be mod xj minus yj whole squared, j equal to 1 to n, and then take its positive square root, non-negative square root, right? So this is a metric, so I have to check the standard properties. The most important properties are the so-called triangle inequality. Okay, whether it is true, right? Now, how do I do that? Notice that d2 of xy equal to this. This is same as, see, without this is same as norm of x minus y whole squared. You will see that, and therefore it's power half. Are you following? This object and this equal to this object. Yeah, and its square root. Therefore, this is nothing other than, therefore, what is this object? This is nothing other than norm of x minus y, right? Therefore, what is the triangle inequality I want to prove? I want to prove norm of x minus y. Give me any z in Rn, whether norm of x minus y is it less than or equal to norm of x minus z plus norm of z minus y. This is what I want to check. Okay, but that is clear because this is a vector. Okay, take this vector as u, this as vector v, then u plus v is this vector, u plus v is this vector. Therefore, we know norm of u is less than or equal to norm of u plus norm of v. You understand? But what is d of xy? This is distance between x and y, d2 of xy. This is Euclidean distance between x and z, and this is the Euclidean distance between z and y. Therefore, triangle inequality for Euclidean metric is also proved. Yeah? Okay. I hope this is enough. I hope all of you understood this. Please go through it. And if this is the first time you are coming with the dot product, okay, spend a lot more time the first 15-20 minutes with x1, x2, xn, y1 to yn and multiplying. Okay, I have done it because I'm experienced, so I do it. But the only way you can become confident is first understand, see what is happening, then pause the thing and take a pen and paper and check it on your own. Okay, you do it only once. After that, you can do my way of doing. Okay, x plus y into u plus v will be x dot y, etc. X dot v plus y dot u plus y dot z. Okay, that kind of thing. You will become very confident. Right? I hope you enjoyed. And this should also make you, if you are following my lectures on metric spaces, this will also help you there. Okay, have a good day. We'll stop. Bye.